so we'll go ahead and start then?
Yeah.
All right, so welcome to our control meetup. So over this meetup, we're going to be going over the new control system, what are best practices in programming, and how to do well in controlling your robot, both in autonomous and teleop, through the use of sensors and this wonderful new Android platform that we're getting this year. So to start it off, we'll go ahead and have Dale Jordan come up and talk about some general control guidelines for you. Hey, Dale.
Hi, I'm Dale Jordan, and I'm formerly an FTC coach and a long-time volunteer for ORTOP, and more recently I've done a few small projects for FIRST itself. I'm glad that these guys asked me to come join them because topics relating to control board are certainly very near and dear to me, and so I certainly welcome the opportunity to go ahead and talk about these things. So, we'll just go ahead and get started here. Now, there are many things that we can talk about on the control board, all sorts of aspects, but I thought I'd pick out a few of the key elements that I think are most important to get teams started. So we start kind of at the top. The control board is relatively new. It's a very comprehensive award that spans many disciplines, including programming, sensor use, electronics. You generally have to have an understanding of physics, and the list just goes on. It's perhaps the most comprehensive award of all of the awards that is handed out, at least for the robot aspect, in designing the robot. And it's really only later that you develop a real appreciation for what the control aspects can give you. So today I'm just going to talk about, so we'll start with the control award description and some highlights on that. There's kind of a realm of possibilities for what you can do in that environment. We'll just kind of touch on that a little bit. And one of the more important elements is a team strategy when you're going about addressing these issues. Then following on with that, I figured by way of a navigational example, I'd go into some of the issues of characterizing the robot and understanding its performance. And then finally, the one thing that many teams dread is documentation, and how that is just vital to the whole project. Those who've been around a while, they certainly, if you haven't spent much time before, as you go to every tournament, read this. So I'm just going to hit the highlights here, the stuff I've highlighted there. Sensors and software to enhance the robots. There are many things you can do that might involve control strategies. A number of teams like to come out there with flashy lights and other things that really make the robot look beautiful. However, those aren't the things that we're interested in the control board. We want to see that translated to what it actually does on the field. Next aspect of that is challenges. Again, this is kind of a software version of the Innovate Award, except it's really more of a combination of the Innovate and Design Awards, kind of as the way this thing is evolving. And then finally, the engineering notebook must contain details about the implementation of the software sensor. It is perhaps more important documentation on this award than any other, because many of the aspects of control are not readily obvious to just a casual observer looking at it. So it's really important that this be documented so that the judges have easy access to that, to kind of refer and help get to understand the things that you've done. Sort of the second page of control award just kind of more details the things that are going on. Obviously the team must demonstrate gracious professionalism. That kind of goes with all awards. There have only been just very few instances over the years that I've seen in tournaments that teams haven't demonstrated that. So that's just almost a given, and by and large, most people really take that to heart. And that's one of the things that make these tournaments just a fun place to be around. The control award is just a little different in that we must submit an application for that. And again, that is to kind of call out and help the judges identify the things that you've done. Again, engineering notebook stuff they call out, and the functionality on the field. Some strongly suggested criteria is that they want to see teams use advanced techniques. They want to see you kind of grow into perhaps things that are not a part of your comfort zone, but kind of grow into new things, discover new things. And the control component should work reliably. We toned that down. I was a part of the committee early on. We toned that down a little bit because a lot of times if teams are pursuing more advanced algorithms and sensor use, until you really get that right, quite often your performance really suffers. So if we see kind of a clear path to where a team is going, we're kind of okay with the performance being downgraded a little bit. It's where we think that the thing that the teams are going to learn by doing this is far more valuable than the ultimate in performance. Moving on to the realm of possibilities, and I love this. If you look at this slide, it's not too busy, it's probably a little hard to read some of the stuff. For the autonomous period, you could go from teams that just don't have autonomous modes at all, and if you were going to take that to the extreme, you would have a robot that would adapt to changing field conditions and always be able to kind of do the optimal scoring, score the max points possible. Clearly that's kind of a dream today, but if you're looking forward as well, what are our possibilities? Similarly for teleop, you may start with just some simple joystick controls and move the robot around, and we see that especially early tournaments with new teams and the like. And then if you go up to the extreme, you've added so many control features that the operator is no longer needed. I would love to see that come about, but clearly these are kind of long-term things. Certainly today we're down very much near the bottom of that scale, and but we kind of see each year that scale kind of goes up a notch or two. And I think one key element in that, as a way of an example, is when things first started out, only a handful of teams, I think throughout the world, used the gyroscope when we first moved over and had that available. And now we see quite a large number of teams that really rely on it, whereas the initial usage was maybe helping out and turning a little bit or something like that. Now teams are using it for all sorts of things and going on to even better components. So we see that bar kind of raising each year. Also to kind of help that along, there are sensors available today that are quite affordable and good that simply weren't available 5-6 years ago. I think the IMU is a good example of this, and like in a manner that gives you better performance. So having these lofty things to look at, there are many ways to go in that direction. I think all of those are celebrated, viewed quite favorably from all of this stuff. So there's plenty of room for growth, and we'll see that continue on for the next several years. For teams starting out, I've seen a lot of teams where they just sit and kind of tinker around with things and the like. And sometimes when you don't know what to do, that's the best thing to do. But probably early on, it's quite useful to kind of develop a strategy. The teams that I've seen do best are those that each year they kind of set goals. Also, in addition to more or less team goals, it's quite helpful if each individual on the team has some personal goals, some things that they want to achieve throughout the season. I found that with my old team, when the kids had personal goals, they tended to work a lot harder and a lot more diligently than when they were just kind of left to meander around. It's a good idea to consider both short and long-term goals. Many things here to do relating to control strategies you can't expect to really learn in 1 year. So taking a long-term approach to that, saying this year we want to accomplish so much and then move on from there for the next year. As we kind of look at robot performance, again, if you're a new team, you really don't want to be trying to do everything at once. Set some modest goals and then kind of grow into the more complex solutions that you can manage. Techniques to use, certainly looking at sensors. Early on, you might want to decide if you just want to use kind of the common legacy type sensors and some simple types of algorithms and stuff to kind of control them. Or maybe when you kind of have a good grasp of that, you're ready to move on to the more advanced techniques. And usually these advanced techniques involve a lot more effort to get those to work right. Let's see. I think going on here for the techniques, certainly you don't want to ignore the things you can do in teleop. I've seen over the past few years where the game challenge has limited the number of the game objects you have that you can contain at once. Teams have gone out and they've done automated ways of determining when they have the max number of these items. And then they signal the operator from afar. And that's kind of enabled that so they can open up and go through and work on the fields where they don't have good visibility of what their robot's doing and just rely on the signal for all of that. Also, there are some other things where if teams want to monitor the internal state. One good thing to do is like detecting when your motors are stalled out and then shutting power down before they burn up. Things like that for prevention of that. I certainly think that coaches would like to have that happen. It saves on their pocketbook and buying new motors. And then I think finally moving down here, kind of the documentation. Again, I'll cover that more later, but good documentation just doesn't happen. You really need to come up with a plan on how you want to carry it out. I don't know of very many teams or kids that they live to document their work. It's something that really has to be kind of a learned behavior, and that takes effort to do it. Certainly, teams that have put in that effort, they're generally well rewarded, at least with feedback and the like from other teams and the like, and many times they'll walk away with awards at tournaments. Certainly when you come to the characterization and testing, need to be looking at things like, well, how well does the robot perform with different field conditions? I think last year in St. Louis was a classic example. The pit area was on a very firm floor, very fine carpet, mats were on there, and it's on a very soft carpet. And robots these days tend to be of the heavier nature. So, you might think, well, just what's going to happen to that robot and how is that going to affect performance? I know several teams around here that could probably talk at length on how it affected their performance. Another thing to be aware of is things like the lighting conditions. Generally, these areas are pretty well lit, but not excessively so. But some different lights and stuff have a different IR component to those. So with now the beacons and stuff being in the IR range, that can affect your ability to sense where the beacon is on the field. Some teams, again, in St. Louis were discovering that because the lighting was quite different. Some other things to look at for how does your robot behave with varying battery conditions? I know certainly the heavier robots, especially if they're running on softer fields, they will pull a battery down during a round of competition. So understanding how your robot is going to behave with various battery conditions is a key element. So these are kind of some of the things that, as you're starting through all of that, you want to think about and come up with a plan for testing and the like. Not kind of this goes through really focusing on the characterization of your robot. And rather than talking generalities kind of as I've done, let's focus on kind of a specific example. So in this thing, I picked our Ortop BiddyBot, which is our 3D printed bot, as a good robot to start for an example. It's quite different than than a typical Teams robot will be. First of all, it's small, it's got a narrow wheelbase, it's lightweight, so probably the things you're going to see here for this robot's behavior will not match your Teams robot at all. And to kind of go with all of that, we just wanted to do some very simple tests and go through the process of that. So here's a picture of our BiddyBot here from the top. And one of the things that you want to do in this testing is kind of characterize the errors that accumulate over time. So there are kind of three errors there. So you're going to have, in the direction of travel, you're going to delta X error, and side-to-side movement, kind of your delta Y error, and then the orientation of the robot. And so these, in a dead reckoning situation, will tend to just continually get larger. You will become, with each move, you will have less certainty as to where you are. So as our simple test going on, we wanted to, okay, I've kind of covered all of that. So we just want this robot to go travel in a straight line and stop. We'll put a piece of paper down, tape it down on the field, and we're going to mark the stopping position very carefully each time. And then just go ahead and go through this for 10 times just to kind of get a sampling of the spread pattern of what goes on there. And for this particular robot, this is what we come up with. So it traveled 5 feet, and we marked the spot on the field and then kind of outlined that. So what we see there is we have a little over an inch error in the direction of travel. That's not too bad, especially with the new system and the relatively slow update rates that it has. And what we see, nearly a 5-inch side-to-side spread. That's simply with just straight dead reckoning. We're turning the motors on the same each time. So we get quite a bit of this. So things that we look at that, we say, okay, if I'm trying to hit a target that's near that distance away, and I have to be within an inch or two, what are my chances of being able to use dead reckoning to accomplish that? They're practically zero. So while this is not going to give you the worst case errors, it kind of gives you a sense of this is how my robot performs. So yeah, I've kind of covered all these other things that are related to that. So we have our straight test kind of done. Then the next test is we kind of want to examine what happens when you turn, the robot turns. So we did this again, and we got a different spread pattern. Actually, it's surprisingly linear. The fact that this robot traveled a total of 10 feet, it's very close to just doubling the error window with that turn in the middle. That I found was a little surprising, and as we kind of go on and look at that, I would have expected that error pattern to be more of a rectangle, because we had the long dimensions of the errors now turning and it became a short dimension. Certainly one of the things in the turning using odometry, as I incorporated the errors that had accumulated into the turn. So this probably translated into the fact that the other error, the shrunk in the other dimension. When you look at things like that, in this case I look at that and I go, oh, that's something that I want to investigate further, because it doesn't fit my model of how the world should work. And you kind of keep going through these on all of this stuff. So that was one of the, that was a key thing there. So that would tell me to go ahead and go through and do some more tests if I cared about straight dead reckoning. Well, one of the things I know for dead reckoning is that's probably not a good long-term solution for things. So I might choose to say, okay, well that's interesting, but let's move on to the next level. Some things here to think about too with that turning. Small errors in turning can translate into much larger positional errors. or like a 1 degree will translate into about an inch over 5 feet. Again, this is kind of a conservative estimate of performance. Your typical performance might be worse, and there are other factors that increase the errors. For this simple test, basically, I just turned the motors on and turned them off. I didn't mess with anything. So if you want to improve the performance, you might want to consider shaping the way that power gets applied to the motors. So they start up a little slower, a little smoother. Same thing for stopping. These would be things you could do and see what kind of improvements you get. Use feedback in the traveling, such as a pin controller, to keep the wheels turning at the same amount. Also, especially with larger robots, they build up quite a bit of momentum. So when you stop and turn, things like that, you may want to pause a little bit to let this momentum settle out to get better performance. These are just all kinds of things to think about. But instead of spending a lot more time on that, I thought I would just move forward and do some of the things that many teams have discovered, that using a gyroscope goes a long ways to help improve your performance. And with the new system, not having a lot of stuff on hand, basically I thought, well, I'll just take some existing things that work. I was getting ahead of myself. First, the gyroscope, it measures the robot turn rate. So you need to integrate that to determine the robot's orientation. That's an angle relative to the field, so you would expect that you can correct over time for errors that build up on that. You might want to use it for driving straight, and also to improve turn accuracy. The thing to remember here is that it will correct for orientation errors, but not necessarily your XY position errors. You know, keeping the orientation correct can certainly improve your positioning errors, but it's not going to correct for those. So I thought for this simple test, I would just go grab a high-technique gyro sensor. I have those laying around, and I know, many teams have those, and just plug it in as a legacy device. I went and I figured, well, I will just modify an old and well-tested NXT algorithm with the gyro. So I went and pulled the last time I looked closely at this stuff off of my old team's robot. I think that's about 7 years ago they did that. And that testing and the stuff that they did with the NXT, they showed that gyroscope, the drift and stuff that normally is associated with that, was stable for the 30-second autonomous period. And it did a reasonable job of accuracy for maintaining the curve, the turns. So I figured, well, I'll just convert that over to Java code and make the necessary corrections. And we'll be off and running, and then I'm just going to go out and measure the improvements in navigation, and I'll feel like a very happy guy. Well, it didn't quite work out that simple. When I ran out of time to work on this, the performance was consistently worse than just normal dead reckoning. The operating conditions are very different in this new environment. First off, the robot mechanical design is quite different. This being a small robot and very, very light, it tends to vibrate a lot because it has omni wheels on the back of it. And as they're beating on the map, that produces a lot of vibration in the robot. So that could certainly be a source of the problem. I didn't grab the same sensor. I don't even know where it is on the robot we used 7 years ago. So there could be a wide variance in the quality of sensors. So that is also a possible source of that. The FTC SDK, it does non-uniform sampling and at a relatively slow rate. It's like when you connect up the motor controllers, the servos, and the like, you're running at a 50 to 60 millisecond update rate. You compare that to the NXT uniform sampling rate, where we were able to update the gyro values every 3 milliseconds, and quite reliably at that. So these are some big differences to consider. Certainly I believe the results that other teams have had over time, the gyros really do improve performance. At this point I realize it's a very hard problem that's going to take a fair amount of study to really solve it. Now, if I were a team member, I'd be thinking very hard, what are my next steps? So, you know, is this a problem that I want to continue to work on? Do I want to maybe look at other types of sensors, like the inertial measurement units that are now available that incorporate many sensors? Certainly one of the things I could do to get away from this non-uniform sampling stuff is if I go buy one with a built-in processor, it has all the algorithms implemented, and now I can just look at the numbers that I want to see. You know, that might be a much better approach, a way to spend my time. So these are all engineering decisions. From a personal standpoint, I'm really curious as to why this doesn't work that well. I expected much, not necessarily really great performance, but I expected much better performance than I was seeing. So the engineer in me is very curious as to understanding why. But anyway, these are decisions that as a team that you need to make on how you go forward. I have seen many teams in the past when they've looked at sensors and they were in situations like this where they don't work, they just say, oh, we tried that, didn't work, moved on. The teams over time that tend to really excel at this kind of stuff are the ones that are very persistent. Okay, it didn't work, now let's dig in, find out why it didn't work, and keep moving forwards. So anyway, some of the other advanced navigation things that we might want to consider is we really want to know our position relative to other objects on the field more precisely than dead reckoning can give us. Some other ways to do that is good ultrasonic sensors can help do that. Some of the new ones like Robotics, they will measure down to 1 millimeter accuracy. They also have temperature probes on there, so they're measuring air temperature to even compensate for the different environment conditions that you're running in. That looks very good. Actually, I'd like to get my hands on one to just see if it does work that well. You've got to use these things when you have a known clear path to the object. That's a very good way to do that. Now, you won't always have that, so you're going to have some sophistication in your algorithms to know when you can trust these sensor readings, and when you can't trust them, then maybe you have to rely on dead reckoning techniques. So these are some things to think about as you go forwards. And I think that if I were actually trying to develop a robot, I might not spend so much more time on trying to sort out all of my issues with dead reckoning, but I might start looking at some of these more exotic things and spend my energies trying to make that kind of stuff work. Then probably going on to our next topic, the control documentation. There's really kind of two elements of that. One is the engineering notebook, which was alluded to in the description of the award, and then there's the submittal form, basically the content or summary sheet that that is being required that teams are required to submit. The summary sheet first is put out, the format for that, and I think with some of the experiences we got, we're going to look to change that. So I say keep an eye out for the new formats on that. But if we start with the engineering notebook, since that's the predominant one, the kinds of things that judges are looking for that, especially with the control award, is we do want to see your journey. That's very useful to kind of see how you've grown, what you've discovered and learned. Now, I know documentation is kind of a difficult thing to get people going on and to keep up to date, but as serving as a judge in the past, when I've seen a team that's done a good job of that, it's very nice to just sit down and read through and kind of discover what they have learned. So in general, when you guys do go to the work, there are people on the other side that you don't see a whole lot necessarily. They do appreciate that work. clearly document your strategy and goals. That's one of the things that, as we're looking through, not necessarily the team that's accomplished the most in the world, but you know, if you've set some realistic goals and you've stuck to those and you see the progress along that, I tell you, that puts a real smile on many judges' faces. They love seeing that. One of the things that is very nice to do that we don't see enough of is to document the sensors you've considered, you know, what they're good at, what they're not so good at, why you chose to use them, things like that. Again, the same thing with the algorithms. And certainly like I did here with the example on characterizing simple navigational issues, we love to see that. That's very important to see that in the journey through how you're doing things. For the documentation for the submittal form, we had a very special team of judges last year at the World Championship, and we were trying out some new things, a new judging process for the control award. And one of the judges especially took some detailed notes, which were just absolutely wonderful. A big part of that was what we would like to see teams do better at. And so hopefully that will get published in some form in the game manual so that teams can see what we'd like to do that. But kind of in a nutshell, when you submit this control form, we want to see the bottom line up front. We want to start with a list of the most impressive and important features in your control system. Basically, tell us what is really cool about it, right up front. That's what we want to see. Then you kind of follow that with kind of the sensor list of the things you're using, how you're using them, purpose for that. Also key algorithms and where you were using those. We kind of want to see that. And this doesn't have to be, we're not looking for a detailed write-up on all that with a lot of verbiage. The thing to keep in mind is that judges only have so much time in the day that they can spend with each team. So the more effective you can communicate all of this and save their time, it gives them that much more time to look more deeply into the stuff you've accomplished. And then again, what is currently there that we're requesting teams to do is just diagram their autonomous paths. So we actually want a little bit more I would like to see a little bit more documentation in the future. And that all come about from sitting in a room in St. Louis for several days, looking through the team's work for Control Award for all of the teams at the tournament, 128 teams. So, so these are some things that teams to think about doing. How can you communicate with the judges? One of the most important thing is when you're putting this together, if you will sit back and put yourself in the judge's shoes and say, what would I be interested in looking at here? What is going to help me fall in love with your work? Again, we want to kind of go back to the engineering notebook from this stuff, so having a list of your sensors and algorithms, and then with pointers into pages and stuff on your engineering notebook that will just direct us right to the spot where we can discover much more in the detail on that. Also to go with this control documentation, and I'm seeing quite a number of teams do this now. I think in the inception of all of this, a couple of teams did it, but the word is leaked out. And many teams are taking the extra step at putting a lot more detailed information and adding that to the end of the submittal form. And I will tell you that that goes over extremely well with the judges. This is kind of free form. Every team kind of has their format for what they feel is important to convey to the judges. One of the most useful things about that is that it is all encapsulated in one place. The judges don't have to go get up and find the engineering notebook and thumb through the pages to get it. It's all right in front of them, and that is well appreciated. The work that teams have done on that, I think, has been very well received. So, so since the cat's out of the bag, I feel comfortable in sharing that because the judges would simply like to see more of that kind of work. Now again, this is all optional, it's not required. Certainly in the early parts of the season, qualifying tournaments and the like, teams are very busy. You know, you're very busy getting things to run, and the documentation just may not get there. If the documentation is not, you know, super smooth or anything like that, that's just fine, especially at the early tournaments, I say. The judges will take their time to kind of discover what you have done with the amount of time they have. So really the effects of all of this is you're just allowing them an easier path to discover really all the cool stuff you've been doing. And with that, I think I've probably talked enough on various aspects of that. So to quickly summarize, develop a clear strategy. Start simple and evolve as your understanding grows. Carefully test as you go. That can shed so much light on actually fixing the problems and moving forwards. And then document, document, document. I think maybe all of us that didn't develop good documentation skills early in life, we're kind of hoping that if we impress upon people at this more formative age, that becomes a natural part of their behavior, that they will do better than we do in the future. So with that, I'll open it up to any questions people may have. Yes?
I have one question. First of all, nice talk. Thank you for that. So talking about the sensor and the using of those sensors, you has some of the example, but I don't know this year, at this moment we know how much of the sensor and external microcontroller is allowed in the competition, because the game menu part one does not very clear about what is allowed, what is not allowed. In terms of, for example, the IMU and some microcontroller system like the Arduino. Do you have more information for that?
The short answer is I have no more information than you do. As I read that, I have all sorts of concerns as well. When the Q&A forum opens up after kickoff, I think those are really important questions to be asking the game design committee. And from past experience, I would say don't read anything into these rules. You know, if you're trying to get ahead of the game and stuff like that, be very careful about reading anything into these rules. More than likely, they're very close to what they expect them to be. I would say that in my interpretation of those is that you would have probably, I read that as you couldn't add things like Arduinos and stuff to enhance your sensor performance off board. So, I mean, but these are really good things to talk to the game design committee about. I think going along with that, since this is a very new platform and we're already seeing some evidence that, okay, it's got a much slower sampling rate, it's not uniform, that can present problems, especially for things like the gyroscope. That if you have issues coming up, that you want to clearly state the problems and perhaps why you would like them to adjust the rules or what have you. That's probably going to get you a lot further. If nothing else, you know, change tends to move very slowly as they change things. I know they probably thought long and hard on what they want to allow this year. So I would say stay persistent. You know, do like they do in government and politics. You know, if you don't like the laws, you don't like the rules, you know, go out and seek change. Clearly in the first environment, though, you want to make sure that you're doing it very respectfully and gracefully. But be persistent over time.
Thanks. Just a little comment, because we are in the stage that last year is a rookie team for our team, and this year second year. So we have been passed to the kids to using more microcontroller and then using sensors. But at this stage, we have invested those and experiment on those. And then later on, if we told kids, sorry, you cannot use this, this is a lot of encouragement. So I try to prevent that to happen.
I know that would be certainly a frustration point from my standpoint. If I spent a year or two studying all this stuff and growing to the point where now I can really effectively use this and be told I can't, I would be very frustrated with that too. I think that would be a fair thing to convey to, if my interpretation of the rules are correct, that would be a very fair thing to convey to the game design committee, especially when there are really two things going on here. One is that for this award, teams are being encouraged to go out and use more advanced techniques to learn these new things. And the other, certainly on the mechanical side, over the last few years, first has been opening it up to more and more things that you can use and be creative with in developing your robot. And this would appear to go counter to that.
Thank you.
Yes?
Do you have your little mini bot with you that you can show off for us?
Yes, I do. I'll grab it here. I'm not sure where we have a good camera angle on all of that, but I'll just kind of set it up here. Yeah, now this thing was with the new Android development system we got this year. Ortop really needed to upgrade their demo box, and we kind of looked at the condition they were in, the number of parts we had, the number of systems we wanted to put together, and of course being a nonprofit, money is always an issue. So we just explored some possibilities to see what we could get by with, and realized, we could probably put everything in there we need for demonstration purposes and just 3D print it. The 3D printing costs for this little robot are on the order of about $20. It takes probably about 40 hours of training time to do that for all of the components. Even though it's mostly done with the PLA, there are some different materials used for the tougher components we need. And there's some flexible PLA stuff for mounting the phone, things like that. And we figured that in worst case, if we take them off the shows and demonstrations and they get heavily used, we have to put in a new one. It's not just desirable to keep doing that, but it seemed like a low-risk approach for us to go ahead and just put something together for show and tell. And so far, it's been at several events. We've got a fleet of 6 of these. We have run it now 3 different events. One was the air show recently with 100-degree weather outside, and they stayed up and performed quite well. One team that took them to demo, they requested to borrow our robots, these robots, as opposed to their own demo bots, because they were just simply easier to set up and use. So that really goes forward to what the first intent was, to move away from field control system and the like, because basically they just take these there, they turn the phones on, turn the robot on, and they're up and running. So that's a very, very positive statement of what the first has done here. The fact that these guys just want to take these and go with them because they're still living on the other control system for their others. Yes?
In the presentation, you mentioned that the sampling rate in the FTC SDK is really slow. Do you know of anything that we would be allowed to do to modify the FTC SDK as it is?
That's a good question. No, I don't. Like I say, I follow the forums just like I know a lot of other people do. I have no access to any additional knowledge. I think if you're, really fast about update rates and stuff, it might be looking down maybe into the capabilities of the controllers from auto robotics and stuff. And I would guess that given all the things they're doing, if it were reasonable to go much faster than that, they'd probably be doing it. So what we have to work with and do here is, I don't have any inside knowledge of that. It's just going to be different than the existing platform. Now before, I sort of said that was kind of slow, but in all honesty, probably is more than adequate for 95% of the teams. It's when you get into the control elements and trying to do, fire control feedback systems and the like that this kind of environment could, I say could, doesn't necessarily, could hamper some performance issues there. Clearly we were, if you had analog sensors with the NXT, it was certainly possible to run tasks that would go out and sample your sensor every 3 milliseconds if the sensor would support that. In the case of the high-technique gyro, that's exactly what our team did 7 years ago. They give them lots of averaging to reduce noise effects and the like. And it worked, it worked okay back then. So it might also mean that get around that, you are forced to go outside of other manufactured sensors. I believe the rule says you're not used, almost any manufactured sensor. It might mean that you have to go out and buy sensors that have already the built-in processing already there, so that you can stay within the rules. Again, all of this kind of remains to be seen. It's all new to all of us. To me, being an old-time control person, I look at that kind of rate and I get a little scared. But if you sit down and work with the file, we'll just see how it goes. I would say stay tuned to the forum and other means of communication, because as a whole FTC community, we're going to be learning this all together. Is that it?
So the one thing that I would say is, if you've seen the recent forum posts, one of the things that they point out is the reason why the legacy controllers performs lower than the regular controllers is because there's a loop that switches between read and write modes, and it takes about 17 loops before it will switch from one mode to another, and they do it because the controllers cannot be in a simultaneous read and write mode at the same time.
Yeah, so lots of things to learn and discover, and that means you just start the legacy mode. At least with the gyro I was only using it in read mode. So unless there are things going on behind the scenes that it has to switch that I'm not aware of, I shouldn't have been limited by that factor.
Right, but we don't know, because you have to characterize that, and that's part of the discovery and growth that teams will have to do.
Yeah, and certainly one of the things I did when I did this navigational characterization is I figured, okay, it was the same kind of thing that we teach coaches who credit files teams and stuff, done this kind of stuff a million times. I honestly thought I was just going to sit down, and in a few hours I'm just going to go through it, take my pictures, and put this together for the presentation. It didn't work that way. So, and that is by no means an indictment that the new system is bad. Things are just different. And the things that we've grown accustomed to, at least the experienced teams, you may have to learn a whole new set of behaviors. It's going to be an interesting ride. Yes?
Maybe we have time, right? So, I'd like to know a little bit more about your experiment. So your comparison point is your first experiment without the gyro sensor. You just using the encoder to control how much you want to go, and the turn also is controlled by just encoder, the motor encoder, right?
That's right, yeah.
And then as comparison, when you use the gyro sensor, so how do you use the gyro sensor?
Well, what I did for the gyro sensor is when I move forwards, I basically put a feedback loop in where I sample the current angle value of the sensor and then fit back a part of that in the system which has motor powers. And when it didn't work initially, it's, the first time I had all these parameters out of whack, so I varied all the relevant parameters up and down. And the interesting thing is that I saw almost no change in performance.
So the slowdown is just to make the robot go straight?
Yes.
Okay.
Yeah. It's sort of like if you're an FLL environment, it's sort of like line following, but using gyroscope. It'd be like a P-line follower, but using gyroscope. It's about as simple as feedback system necessarily expecting that it would give optimal performance, but I was expecting it to give better performance than simple dead reckoning. And in reality, what I was seeing is things that was 2 to 3 times worse. That really tells me that as I was varying parameters, that I haven't localized or discovered the key element that's causing this behavior. There are many other things to look at and isolate that. And perhaps this is an example which is sort of incomplete. It's not like a normal TV show where at the end of that hour, you know, everybody's problems are solved and everybody's happy again. This is more of a typical engineering environment as well. After my time is up, I still have more questions than I have answers, and I certainly have more questions than I started out with.
When you make the left turn, you also use the Java sensor?
That was the intent, but since I didn't have driving straight working very well, there was really very little need to go to the next level. Yes?
So, I'm a parent from the robotics team, and I was wondering if I want to learn more about the SDK that has come out, where would I start from?
I would start, well, there's a sort of like this data installation manual that comes with it to install everything that goes with it. And near the end of that, they've got some good initial examples of kind of getting started and what to do. That was my initial playing around with it, is I just copied one of their operating modes and give it my own name, and then I started tweaking that a bit. And, you know, I started feeling pretty good about it. So I think that's probably a good place to start. I know that first is contracted with, I believe, what is it,
Intelitech.
Intelitech, yes. To do the documentation, you know, that will be coming out here in the not too distant future. So there will be plenty of information there, I think, to get people started.
Yeah.
Okay.
So thank you for that, Dale. So we'll be moving on to our own presentation about some other stuff about the control board and sensors and such. So we are.
I'm not seeing on the second screen.
Yeah.
Duplicate the screen.
Oh, okay. You're seeing this. Alright, so we're Team 4855, Batteries in Black, and we've been around for 4 years, and we've had some pretty good success with the old control system, but the new ones, we're starting off just pretty much where everyone else is, don't really know much. And we're also trying to learn as fast as we can about what we can do on this new platform. So the control award, mostly Dale did a really good job going over most of it.
We're still not seeing the screen.
You're not seeing the screen?
No. Just do a duplicate.
I'm on duplicate right now.
Okay. We'll go outside. now it's come up.
That's good. Okay. Alright, so the main parts of the control boards are using sensors and software to enhance your robot performance, both during the autonomous period as well as the teleop period. Using innovative solutions in autonomous and mechanical systems, all with intelligent controls so that you really set apart what you did from other teams to really show that you were one of the best teams at the competition in terms of control, and being consistent across many different times, because the whole point of using sensors and intelligent control is to make sure that you get consistent results. If your autonomous works 1 out of 5 times, then maybe it wasn't worth all of those sensors. The purpose of using sensors should be to produce the same results over and over again. And obviously, documenting all of this in the engineering notebook and producing a good content sheet is going to be the best way that judges are going to be able to learn about what you've done. Otherwise, they're oftentimes left in the dark and wondering about exactly what you've done only after the short amount of time that they get to talk with you. If they're really interested about your control or your control systems, then their best resource is going to be your engineering notebook and how much effort you put into documenting everything that you did. Right, so the new system is a Java-based Android platform powered by a Qualcomm Snapdragon, and there's also a few sensors built into the phone. For example, we have the 2 phones with us right here, the ZTE Speed as well as the Moto G 2nd Gen. So with the ZTE Speed, you get a ton of sensors. You get accelerometer, compass, I think, and then you also get a few more that maybe you won't be using, as well as a camera that we hope we're going to be able to use. And whereas in the Moto G 2nd Gen, you also get a gyroscope on top of everything else that you get in the ZTE Speed, if you get the international model. If you get the US model, then you may end up without a gyroscope, even though it's $5 or $10 cheaper. So the big difference between the phones is that, for one, the ZTE Speed you can get for around $50 at Best Buy, whereas the Moto G 2nd Gen is no longer being produced, and it can be a lot more expensive, and sometimes you might have to buy it from international markets to get it. However, it does come with a gyroscope. And as Dale was talking, the sampling rate right now for the high-tech gyroscope is pretty slow, whereas with the Moto G, you have a very, very high sample rates. Some of our initial tests indicate that you're getting a sample rate that's probably better than what you used to get with the NXT. So if you can effectively use the phone's gyroscope, you may be able to get better results than what we've been able to get in previous years and have better control over our robot. And this is also going to be a lot easier to use in your programs because the sensor is built into the phone, instead of having to use an external sensor and interface with that and all kinds of issues that may arise from that. And you also get to practice as you play through Wi-Fi Direct, meaning that you no longer have to rely upon somebody else setting up a system and hope that they've configured everything right for you. You get to use 2 phones, a driver station and a robot controller, and you practice the exact same way that you're going to be at the competition, so that this way you're used to controlling your robot the way you will at a competition, whereas in previous years, sometimes teams don't even know how the Samantha works until they come there. So now you will know that your robot works really well with the official control system. Now, you can use either Android Studio or the MIT App Inventor to make your programs for this year. MIT App Inventor is probably going to be a lot easier for some of the rookie teams or teams that aren't overly fluent in programming yet. And it's a good way to get started with programming. However, Java is going to be much more versatile. There's many more libraries that are available to you. There's much more support. And it's oftentimes easier for longer programs, especially when you have lots of variables and if you want to create a bunch of objects that you want to use in your program. So yeah, there's 2 types of Android devices that you can use, and there's the legacy controllers as well as the modern robotics controllers. So one of the obvious advantages for the modern robotics controllers is that they're all designed to work together, and modern robotics claims that they are a little bit faster to use the newer control systems as opposed to the legacy modules. And however, if you are an older team, you may want to go with the legacy because it is a much cheaper solution if you already have the older motor controllers with you. So just in case you guys haven't seen the core power distribution module, it basically has a bunch of power outlets, a bunch of USB outlets, hooks up straight to your phone and a battery, and it also comes with a switch and a fuse, so everything bundled together for you to be using. And okay, so yeah, so the core power distribution module is the main thing that everything connects to in this year's model. The phone plugs straight into here, and all the commands travel through this module. And it sends commands through USB to all of the existing modules, including the core device interface, which is going to be used for sensors, the motor controller, servo controller, and however, most sonar sensors have a dead range between 10 to 30 centimeters, depending on which model you're using. So it'll be interesting if we can combine a proximity sensor with a sonar sensor to eliminate dead ranges and detect objects in a wider range, so that we can detect objects that are many feet or yards away from us, as well as within centimeters for fine alignments. The touch sensor, in my opinion, it's $20, $25. So if you want an easy to use plug and go touch sensor, this is going to be a great option. But if price is a big concern for you, then you can look into custom touch sensors, which you can get from $1 to $10 depending on the maker, and plug those into the core device interface, and you can get many, many more for the same price. That way, however, the modern robotics touch sensor is going to be easier for just one use. And the custom sensors and other sensors are pretty much any other manufacturer that makes sensors. You're going to be able to plug these in directly into the core device interface, as we used to be able to plug those into the prototype board. Now, the only question about whether you're going to be able to use other microprocessors is primarily due to one rule that states that the only language you can use this year is Java, and that you have to code through App Inventor or Android Studio. Now, we're not sure if this definitely means that we're not going to be able to use any Arduinos as we were able to in the past, but I assume there's going to be a lot of clarifications in the FTC forums in the near future, and be sure to look to those to see and make sure if we're able to use an Arduino in the following year and similar microprocessors. So the two software options that I've talked about are Java and App Creator. So Java has many more libraries. This means that if there's anything that you want to do in Java, if you want to manipulate data in a certain way, if you want to run a certain algorithm, chances are, since the language is so big and so many people use it, somebody's probably already done that, and there's probably a library out there that you can grab and integrate into your project as long as you give them credit. Now, this will make it easier to do things that people have done before you, so you don't have to reinvent the wheel, and you can spend less time doing low-level code and more time making higher-level improvements. And there's also more support for the Android platform for Java, since MIT App Creator is relatively new and not as advanced as the Java platform. Also, it allows for easier encapsulation of variables so that you have an easier time managing all of your data, your variables, all of your objects in Java, instead of App Creator and dealing with tons of data wires everywhere. However, the one advantage of App Creator is that it can be easier to use if you're not familiar to programming, since it's much more intuitive feel to it. And as far as innovative thinking and control goes, the main idea is to think outside of the box. Don't be doing what everyone else is doing. What this means, you're going to have to be able to decide for yourselves and really impress the judges with something that you've done in a unique way that no one else has done. So really, no one else can tell you what innovative thinking is. You have to go and find it for yourself and prove to the judges that what you did is truly unique to your team. And for documentation, it's important that you document what you do in the real way. Now, these are some comics that don't just document what it should do, document what it actually does, because a lot of times people will go ahead and just say their code does what it should do, even though it does something else. All Alright, so the control award content sheet looks something like this, at least with for last year. We're going to have an updated map for this year. So the idea is you go in and show what your robot does, what path it takes in autonomous, and a brief description of your autonomous program and your teleapp program. And then oftentimes you're going to provide references to your longer in-depth summary that oftentimes comes after it, or references to your engineering notebook so that the judges can go ahead and get a more in-depth view of what you did if they wish to. And the conclusion is to really experiment. Everyone is going to be new to this Android platform, and the only way that you're going to get familiar with it is to be playing around with it yourself. And once you really just try a bunch of different things and document what you're doing, then you're going to understand for yourselves how, or what are the good things in the new system, and maybe what are some of the disadvantages as opposed to the NXT system. And you'll get a really great feel about hopefully what the advantages are in the new system, and find some innovative and creative ways to tackle next year's challenge with the new control system. All right, and be sure to, and this brings us to the end unless you have any questions for me. All right, no questions?
I have one comment.
All right.
I loved your slide on thinking outside the box.
Thank you. All right.
Hi, is Batteries in Black source code open source on GitHub?
I do not believe we are open sourcing our project this year. Alright. So thank you guys for coming to our meetup. Be sure to check us out on our social media and updates for our next Supercharged seminar that we're going to be having. We're likely to have one within the next 3 to 4 weeks, so check out our Facebook page, our website, and our Twitter for updates on when and where that's going to be and what it's going to be about. And additional resources that you can use to find out more about the control softwares and all about FTC. The US First website, ORTOP about local events, as well as the Oregon FTC Facebook to learn more there. The game manual for all the technical definitions, as well as the forums for all the updates, as I'm sure there are going to be a ton of with the new control system. And that's all for today. Thank you for coming.
Thank you.